好。对啊，那可以了吗 ？OK， 好。OK, so let's continue. Okay. So, oh, by the way, one student asked me about the how the visualization of the programming assignment should be. Okay. Because there are different ways to do that. So I leave that one to TA because after all, they have to grade the programming assignment. But there are many different simple ways. You can output the your tree, okay, by text, okay, text format, or you can output your tree in a similar in a manner defined by yourself in a CSV file. Okay, either way, I mean, I think as long as it's you give like a proper definition of your output, I mean, we will take it. Okay, we'll take that. But I will leave that one for the TA to answer. Okay, because like it looks like you some of you send a question to the undergraduate TA, but it's supposed to be the graduate TA to do that. So I have I already have like the undergraduate TA to forward the question to the graduate TA to handle that. Okay, 所以你们有回了吗 ？Okay, yeah, yeah. So 你们到时候把那个 announce 一下好了，放在EE class 上面，这样子大家比较知道。Okay. Okay. So back to this single source shortest path problem. Okay. This is of course a particular situation where your graph has no negative edge weight. Okay. So the idea, okay, as I said, it's a greedy algorithm. So you are going to maintain a set of vertices, okay, called S, whose shortest path distance from S are known. Okay, so you maintain this set. The shortest path from the source node to these nodes are already known. Okay, and at each step, you add to this set one vertex, okay, from the rest of the vertices, okay, whose distance estimate from S is minimum. And you will update the distance, okay, estimate of vertices adjacent to V, okay. So this one, if you look at this idea, you will feel that it is very, very similar to Prim's algorithm. Okay? To be very honest with you, yes, it is almost identical. Okay, almost identical. If you look at this sketch, this idea, okay, sketch, it is almost identical. The only difference is that, okay, the condition. Okay, so here is like the initialization. So it's exactly just like Prim's algorithm. You can see that for each vertex, okay, you assign the distance to V is infinite. It's kind of just like a key you assign to be infinite in the Prim's algorithm, right? Initially, okay, and then the S to be empty set. You assign all the vertices to your priority queue. So you see that, okay, this part is pretty much identical to the Prim's algorithm, right? So the only difference, I don't know. Yeah, I mean, it's similar actually. You know, in the Prim's algorithm, you start with one arbitrary node, right? But in the Dijkstra algorithm, you start from a particular source node. This source node is given, okay, at the beginning. Okay, so in the MST, basically you can start from any node. It will not give you a starting node, but so you randomly pick one. But in here, okay, your S is a given, so you assign like the distance, okay, to the source node is 0. Basically, because you don't have any, what should I say, like the shortest path from S to S obviously is just stay there, right? Okay, so distance to itself will be 0. Shortest distance will be 0. Okay, so it is like a pretty straightforward. Okay. So then, okay, what happens is that, okay, as long as Q is not empty, okay, you do the rest. You see, this is again very similar to the Prim's algorithm. So you first get the min node, okay, the node with the minimal key from the priority Q, okay, that node to be U. So initially, of course, the first node you are going to get is S, because S has a key 0, and all the other node has key infinite, right? Okay, so, and then once you get that node, you include that node in the S. S, what is S? S, the set S contains the nodes that you already know the shortest path to those nodes. So the source node, okay, the single node source node, like obviously, I mean, you know, as I said, like, you know, is a given, right? You don't need to go anywhere, okay, just stay there, and that's the shortest path. So you just include the U to be, which is S, to be S. Of course, in the next loop, it may be different. So for each, and then after you include this node, okay, for each neighbor of U, okay, if dV is greater than du plus wuv, then you update the value of dV to be this one. Okay, we call this one relaxation step. Relaxation step. Okay, so this one, okay, because you are updating the key, right? You are updating the key. So obviously, you also need, if that happens, you also need to update the location of the node in the queue, right? So it is implicitly, you are calling a decrease key here. Okay? This is like if the distance to V is greater than, from U, you go from the source node, you go to U, and then if you have an H from U to V, okay, if this is obviously one possible path from source to V, right? So if this distance is lower than dV, then you update the dV. That's it. This is a very simple idea. Very simple idea. So let's look at how this algorithm is executed on a running example. Okay, so this is a graph with non-negative edge weight. Okay, and we have like 5 nodes with like 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. Okay, then let's start with node A. and we'll assign 0 to it, right? And then obviously you are going to update A's neighbor from infinite. Okay, all these other nodes are infinite. You are going to update B and C, which are A's neighbor, from infinite to 10 and 3 respectively, right? Okay, so you, sorry, by the way, you first include A into the set S, right? This line, this line, this line. Okay, so we denote that as we assign a pink shade to this node to indicate that we already know the shortest path to this node. Okay? And then we update B and C value from infinite to 10 to 3. Okay? And then you can see that, okay, the next node you try to extract from the priority queue will be what? Will be C, right? Okay, because C has the key 3, right? Okay, so the next node that you will include to the set S will be C. And think about this. At this point, is it possible for you to have any path like with the path weight lower than 3? Think about this. Is it possible? It is, we haven't proved that yet. I'm just asking you intuitively. Let's take a look. Is it possible? Actually, at the time when C is chosen from priority queue, okay, it implicitly means that from A to C, A is C's parent in the shortest path. This is already known. Okay? Why? Because we will prove that later. But I want you to think about this. Intuitively, it is impossible for, at a later time, it is impossible from the source to C to have the lower path weight. It is impossible. Okay, so anyway, the set S will include A and C. And then once you include C into the set S, okay, C has neighbor B and D and E, right? B, D, and E. And so it's going to update the weight, the key for B, which is 3 plus 4, right? It's 3 plus 4. 3 plus 4 is lower than 10, right? So it's going to relax 10 to be 3. And it's going to update, D to be 3 plus 8 is 11. And the E to be 3 plus 2 to be 5. So it's going to be 7, 11, and 5, right? Okay. And then the next round, obviously, you are going to pick E, right? Because E has the lowest key value, which is 5. And by the way, as I said, at this time, when you pick E, you already know the shortest path. Okay, the shortest path from A to E. E's parent is the previous node. The shortest path. From A to E. The previous hop to E would be C. Okay, because E is updated by C, right? Okay, so you need to remember which node is the one that updated you. the last. Because once you are chosen into the set S, that node would be your previous node, okay, in the shortest path. Okay, so in this case, for E, the previous node will be C. Okay, or put it another way, the shortest path from A to E will be ACE. Okay, so then once we have the E, of course, the neighbor of E is D. Okay, so we need to check. Okay, this is 5 plus 9, so it's 14. And the key for D is 11, so it's already lower than 14, so it remains the same, right? So then, okay, 7, 11, so obviously we will pick B. Okay, we'll include B in the set S. Okay, and remember which node update the B value. Which node update the B value? It was C, right? It was C. Although the first update was done by A, the second update was done by C. The second relaxation is done by C, right? So you just need to remember which one did it to you the last. Okay, so it's a C. So once you are picked here, okay, so you know the shortest path from A to B will be ACB. ACB. And then, okay, for B, it has several neighbors. Okay, it has C, it has D, right? So C, okay, look at here. So 7 plus 1, 8. But C is already chosen, right? So you don't need to worry about it. Okay, C is no longer, on the menu. Okay, you can skip that. But for for D, it's going to be 7 plus 2, so it will be 9. 9 is lower than 11, right? So you are going to update 11 to 9, okay? And then the last one you pick will be 9. Which is also it's also the last one you pick. Okay, so you are done. Okay, and by the way, because the last one, okay, D is updated last by B, right? So you see the shortest path from A to D will be A, C, B, and D. Okay, A, C, B, D. So this is the shortest path. By the way, I want to remind you, take a look. Okay, why do I say the next one you pick, okay, is guaranteed to be the short, this when you pick C, okay, the A to be picked, initially that's a given, right? Everybody know, A has to be picked first. But when you pick C, I told you that the C will be the shortest path. Because think about this. You can see that the key, you see, is 3 and then 5, 7, 9. It keeps increasing, right? Some key gets decreased, yes, along this path. But the one that gets picked, you will see that it keeps increasing. So what I meant is okay, in this round, if this one is the minimum, it would not go any lower than this. Okay? So the rest, okay, we have to prove some stuff. And then we will talk about the complexity, the time complexity of the Dijkstra. Oh, by the way, one thing I want to mention about Dijkstra algorithm is that, you know the name Dijkstra. This algorithm, it is called Dijkstra, right? Okay, Dijkstra is a person's name. Okay, this guy is so famous. Okay, he was in Germany when he grew up. Jewish. Okay, obviously because of the World War II. Okay, Germany kills like a lot of Jews, right? So he has to escape to U.S. Okay, but he was already very famous before he escaped to U.S. Okay, he was like he became so famous in his young age, like about 20 something. Okay, like did I mention to you like which award is like the highest award for computer scientists？ 就是说对我们资工系的人来讲哦，你看物理系啊、化学系啊、医学系啊，他们最高奖项是诺贝尔奖，对不对？对不对？我们都知道诺贝尔奖。那资工是什么？或者说，我先问数学是什么？数学系，因为我自己刚好是数学系毕业的嘛，大学的时候数学系毕业，数学系的最高的奖项叫 Fields Award， 费尔兹奖。OK， 不是那个报道的那个费尔兹哦，不一样。Fields Award 那个 Fields Award 比较更困难，比一般的奖项稍微再更困难，因为它有年龄限制，它限制你拿那个奖项的时候，不但要很强，而且还要我记得年纪不知道是30岁以下之类的，还是不知道多少岁，反正很夸张。对，不过撇开那个不讲，因为我们不是数学系的哦。OK， 资工系是什么奖？资工系的最高奖项叫 Turing Award 哦 ，Turing Award， 图灵奖。OK， Turing Award，Turing 就是纪念那个 Alan Turing。你们有看过那个 Imitation Game 吗？模仿游戏。那个 Alan Turing 哦，就是严格讲起来，人家讲说他 Alan Turing 有讲他是 the father of computer science 嘛，就是资工之父啊，对，所以这个我们的最高奖项是 named after him 哦。那这个 Dijkstra 在20几岁，20岁出头的样子，他才刚拿 PhD 就拿到 Turing Award， 那是很夸张的事情。现在你看到拿到 Turing， 就像拿诺贝尔奖的，大概都4、5岁，甚至5、6岁、7、8岁都有。OK， 没有人30岁拿奖的啦，他20几岁拿奖。OK。那后来因为犹太人嘛，被这个纳粹迫害，他就到美国，他后来一直待在 UT Austin。OK， 你们看那个 UT Austin 哦，为什么 UT Austin 排名那么好哦？其实很大的一个原因是因为他哦，因为 Dijkstra 在那边，他一直在死之前都待在 UT Austin。他在那边待，差不多应该有30年以上，30-40年。他应该差不多接近2000年的时候才过世哦。OK， 等于说你知道196那时候什么1940几年就那个嘛，就第二次世界大战就结束了嘛。然后是1940几年吧，对，民国几年？大概接近1950年了。反正他在那个 UT Austin 待了应该有40多年了。反正 anyway 就后来就过世。然后他是那种做什么领域就是做超级夸张的。对，那个数学当然也有一些数学家是这样子，但是资工里面做各个领域都每一个领域随便做都做得很好的，很少，就只有他是其中算最有名的一个人物哦，最有名的人物。然后 Turing Award 有一个很特别的一个情形是这样子，说那个因为后面拿图灵奖的都需要去，因为要去怎么讲，就是前面图灵奖的人要去投票选下一届图灵奖的。OK， 那所以说呢，那个因为他太早就拿图灵奖了，他资质他辈分很深嘛，很高嘛。那在图灵奖的那些投票者中，辈分非常高。那怎么讲？又在 美国的有名大学，所以他基本上后面所有那个想要拿 Turing Award 的，基本上都会被邀到 UT Austin 去给演讲。OK， 他有一个特别的一个演讲是给那个图灵奖的，有点像是候选人去给演讲哦。所以讲老实话，那个 UT Austin 在这方面还蛮得天独厚的。但当然，他现在已经过世应该快20年了，所以现在情形怎么样我不知道了。但是我知道说，以前我有一个跟我合作的一个那个教授，他以前是在那个就是那个演讲里面帮忙那个就是怎么讲接待那个演讲者的，他就跟我讲说，那个有一些想要拿 Turing Award 的，就是都会跑到他们那边 UT Austin 去给演讲，这样子听他讲的一些故事还蛮好玩的，包括台湾在美国的这个一些老师哦，那个 HT 控哦，都有去过 UT Austin 给演讲，但是他后来没有被选到哦，他没有拿到 Turing Award。OK， 不过对啊 ，Anyway， 就是这个 Dijkstra 非常非常有名。OK， 你们可以去 Wikipedia 看一下这号人物，毕竟在资工系来讲的话，有这么高的地位的人比较少见哦。就是说，能够讲到这种名字的 Alan Turing 啊，然后再来可能就是他了。OK， 就在资工领域来讲 ，OK， 所以先讲一下这个，配一个 respect。对不起，好，我们先休息一下好了，我们再来讲这个证明。